Hello and welcome to this lecture on advanced electric drives. In the last lecture, we were discussing about the unipolar brushless DC motor drive, where only one winding is excited at a time, and as a result the torque production is less. So let us take a look at the unipolar drive. Now here, as you can see that we have a brushless DC motor where we have three windings, W1, W2 and W3, and these three windings are excited from a single DC source, that is Vd, and the three windings are connected to T1, the transistor T1, the transistor T2 and the transistor T3 respectively. So at any given time only one of the transistors will be on, and hence only one of the windings will be excited. So we have the three windings W1, W2 and W3, and the rotor in this case, as we know that in brushless DC motor the rotor is essentially a permanent magnet rotor, which is maybe 2 pole or any even number of poles. And in this case, for a simple brushless DC motor, we can switch the windings in a sequential fashion to make the rotor rotate either in clockwise direction or in anti-clockwise direction. Now here, to make the rotor rotate in anti-clockwise direction, our sequence of switching will be W1, W2 and W3, and these three windings are switched based on an optical encoder which is housed on the rotor and fixed to the rotor. We have an optical encoder which has got three photosensors, PT1, PT2 and PT3, and these photosensors give signals like 100, 010, 001 and so on, and as a result one of the windings is excited and hence we have a continuous rotation. On the other hand, we have a possibility that in a motor we can excite more than one winding at a time, and in that case the torque production will be better, will be more in fact. So we will see a drive where more than one winding is excited, and that drive is called a bipolar drive. So we will now discuss about a three-phase bipolar brushless DC motor drive, where we excite these windings from a three-phase inverter, and each phase can have both positive current and negative current. So this is the inverter structure. We have the two transistors per phase. This for one phase, this for the other phase. And this is for the third phase. And here we have the feedback diodes. The diodes will facilitate bidirectional current flow for an inductive winding, and the current can be maintained. These are the feedback diodes, and we can name the transistor as T1, T2, T3, T4, T5 and T6, and we will be supplying a three-phase winding, and the three-phase winding is supplied from, this is the point we supply phase A, this is the point we supply phase B, and this is the point we supply phase C. Now, how are the phases arranged? The phases are arranged inside the motor. We have the stator. Here the phases are basically the stator. So, we are exciting the stator, and the rotor is essentially a permanent magnet. So, we have 3-phase winding on the stator in a brushless DC motor. The rotor is a permanent magnet, and we can assume, let us say, rotor has got only 2 poles. So, here these are the various phases here, phase A, phase B, and phase C. What about the rotor? The rotor is here, and the rotor is housed with again an optical encoder, as we have already seen. Here also we have an optical encoder, and the optical encoder is arranged like this. So, we have all these 60-degree regions, and for the optical encoders we have 6 photo transistors. These are the holes. In fact, this is the photo transistor, and we can call this photo transistor as PT1, PT2, PT3, PT4, PT5, and PT6. The phototransistors are separated from each other by 60 degree. There are 6 phototransistors. We have in one revolution we have 360 degree. So, the phototransistors are spaced in 60 degree interval, and the optical encoder is constructed by having a disc which is having 180 degree transparent and 180 degree opaque material. So, this part is the opaque region. The light does not pass through this region. This is the opaque region. So, when the phototransistor comes in the opaque region, they are basically covered. They do not give a signal, that is 1. When the phototransistor encounters a transparent region that is not hashed, the hashed regions are actually the opaque region, and in the opaque region the phototransistor gives a signal equal to 0, and in the transparent region the phototransistor gives a signal that is equal to 1. So, at any given time, because of the encoder arrangement, this is basically an optical encoder, because of the typical arrangement of the encoder, at any given time the 3 of the phototransistor will be giving 1. Now, here we can very clearly say that PT1, PT2 and PT3 will be giving signal 1. So, in fact, if we try to write down the signals here, PT1, PT2, PT3, PT4, PT5 and PT6. These are the phototransistors. For the present situation, the phototransistor 1 will be giving a high here because it is facing the transparent region. Phototransistor 2 will also be giving a signal that is high, it is also in the transparent region. Phototransistor 3 will be giving a signal high, and phototransistor 4, 5 and 6 will be giving signals 0. Now, if the rotor rotates in the clockwise direction, the clockwise means it rotates like this. If the rotation is clockwise, we can say that after some time PT1 will be 0, PT2 will be 1, PT3 will be 1, PT4 is 1, PT5 will be 0 and PT6 will be 0. And similarly, we can write down the sequence. After that, we have 3 1s which are shifted here, and then we have this state. After that, we have PT1 becomes 1, PT2, PT3, PT4 are all zeros, PT5 and PT6 are 1. After 60 degree, we have 1 1 here, and then we have 0 0 0 for PT3, 4 and 5, and PT6 is again equal to 1. Then after 60 degree of this, we have 1 1 1, then 0 0 and 0. So it is same as the starting sequence. So what we have shown here basically 6 states, and the state changes after 60 degree because the phototransistors are kept in 60 degree interval and they are stationary. The phototransistor are stationary. The phototransistor receive the light. At one side we have a phototransistor like this, the phototransistor, and on the other side we have a light source. So the phototransistor will give a signal 1 when it faces a transparent region. So in that case, this is the sequence when it rotates in clockwise direction, and the states change in every 60 degree interval. Now suppose we have the rotor, and the rotor here is a permanent magnet rotor, and let us say the rotor has got only 2 poles, a north pole and a south pole, and the rotor is placed with respect to the phototransistor and the encoders in the following fashion. We have the rotor is a permanent magnet. So here is a equivalent permanent magnet we have, and this is our north pole and this is the south pole. So the rotor is placed like this, and it is glued to the disc which is having opaque and transparent region. It is glued to the rotor, and the disc rotates along with the rotor. The phototransistors are having fixed spatial locations, 60 degree in space, but the disc is rotating along with the rotor in the clockwise direction. Now let us say that we want to make the rotor rotates in the clockwise direction. Now to do that, we have to excite the windings. So to excite the windings, we have to switch the transistors. Now this winding A is connected to A of the inverter, and this is phase B. So we can say this is the phase B here, and this is our phase C, and the phase B here is connected to phase B of the inverter. Phase C here is connected to phase C of the inverter, and we can see here that in the inverter the DC source is VD, and in every phase we have 2 transistors. So for example, in phase A we have T1 and T4. So phase A is connected to, in fact, T1 and T4. Similarly, phase B is connected to T3 and T6, and similarly phase C is connected to T5 and T2. So this is T5 and T2. When we excite these various phases, we should make sure that for optimal torque production, the angle between the rotor field and the stator field should be 90 degree, just like a DC machine. If you observe a DC machine, the field MMF and the armature MMF are in quadrature. They are 90 degree for optimal torque production. So we can have the similar condition here. So we will assume that for this particular situation, we would excite phase A, phase B and phase C in such a fashion that the field direction is orthogonal to the direction of the rotor field. In fact, we are aiming at a field which is in this direction, and the rotor field is in this direction, and this angle between the two fields is 90. So when we excite phase A will be carrying current in this direction. This is the direction of phase A current. Okay, let us say it is carrying a current I. So we have applied a positive voltage to phase A, and phase A is carrying this current I in this direction, let us say, and phase B will be connected to a negative bus. We can assume that if the negative voltage is applied, this will carry current into the rotor. So it is I by 2, and phase C is also applied with a negative voltage. So this will carry current here in this direction, and this magnitude is I by 2. And since we have a 3-phase winding, we can connect this winding in star. So if we connect the winding in star, so what we have essentially is this, that these windings are all connected. So phase B, phase C and phase A are all connected. So we have a star connected stator. So in a star connected stator, IA plus IB plus IC is equal to 0. So in this case, if phase A is carrying I in the positive direction, phase B and phase C will be carrying I by 2 and I by 2 in the other direction. So let us see how exactly the MMF is produced. So we have 3 phases here, phase A, phase B and phase C. So this is phase A, we have phase B here and we have phase C here, and these are all star connected. So phase A is applied with a positive current, so it means the current is like this, okay. So it is I, and phase B current is the other direction, it is I by 2 and it is I by 2 here. So when we excite the windings like this, the MMF will be the vector sum of the 3 MMF. We have phase A is excited, phase B is excited, phase C is also excited. So the resultant MMF has to be the vector sum of the 3 MMFs. So we can say that the resultant of these 3 would be in this direction. This is the resultant of the 3 MMF. We have one MMF in A, other MMF along B axis, and the third MMF is along C axis. So if we try to find out the resultant of this 3, we'll get a vector which is along the phase A axis having an amplitude which is 3 by 2 times the MMF of phase A. So this is the MMF, and when the MMF is produced like this, what we have here, we have a south pole produced here and a north pole produced here. By definition, south pole receives the flux, north pole gives the flux. And what was the direction of the rotor? The rotor direction was perpendicular, like this. So this is the south pole, this is the north pole we have on the top, and then here we have the south pole, and south pole attracts the north pole, so there will be a tendency of the rotor to rotate in the clockwise direction. So when the rotor rotates, the encoder position also gets changed. You can see here that we are talking about a bipolar drive. So when the encoder position is changed, initially what we had PT1, PT2 and PT3. So PT1, PT2 and PT3 were giving all 1. We were in this particular situation. Now if it rotates by 30 degree right now, we will be in this particular state 0, 1, 1, 1, 0, 1, 0. So in this state PT1 is covered, PT2, PT3 and PT4, all of them will be facing light. So PT2, PT3 and PT4 will be 1, and PT5 and PT6 and PT1 will be 0. So we will be in a different position. So in that case, what we have a situation, we can say that for the clockwise rotation, we have to feed the phototransistor in the following fashion. So we have the phototransistor is PT1, PT2, PT3, PT4, PT5 and PT6. And how are they connected? They are connected in the following fashion. PT1 is connected to T6. So we have the transistor in this case. So we have 6 transistors. So PT1 is connected to T6. So we will see here that PT1 is connected to T6. PT2 will be connected to T1 in a very sequential way. Then PT3 will be connected to T2. PT4 will be connected to T3. PT5 is connected to T4 and PT6 is connected to T5. Now when we excite a winding say for example phase A is excited either by T1 or by T4. We can see here that phase A is excited either by T1 or by T4. So T1 will be giving a positive current and T4 will be giving a negative current. Hence what we are saying here, that in every winding the current can be bidirectional. By applying a positive voltage we can push a positive current, by applying a negative voltage we can have a negative current. Similarly for phase B can have a positive current. Positive current means current coming out here by applying T3, and we can have a negative current by applying T6. Similarly in phase C, by applying phase C, if we want to have a positive current you can trigger or switch on T5, and if you want to have a negative current we can trigger T2. So we will see what happens in this case, that we are in the clockwise rotation. So for PT1, PT2 and PT3, T6, T1 and T2 are on. So T1 is connected to phase A, and for phase B we are connecting T3 and T6, and phase C is connected to T5 and T2. So in this case T6 is on, T1 is on and T2 is on. T6 is on, so this is on. T1 is on, this is on, and T2 is on, this is on. So here we can assume that the current in phase A is in this direction, it's a positive current, let's say, and phase B and phase C are connected to the negative bus. Okay, so this is connected, so hence this current is I by 2 and this current is I by 2. So the rotation of the rotor is in the clockwise direction. After some time we will have a different situation. So we will have T6 will be covered, T1, T2 and T3 will be on. So in that case what is the position of the MMF? Let's try to find out. So we have phase A here, we have phase B in this case, and here we have phase C, and the switchings have been changed. So this is connected to T1, T4. Phase B is connected to T3, T6. Phase C is connected to transistor T5 and T2. Now we have T1, T2 and T3. Three transistors are now on. Now in this case, T1 is on, T2 is on and T3 is on. So it means phase A and phase B will have positive current and phase C will have negative current. So it means phase A current will be positive, phase B current will be positive, but phase C current is negative. So this is this current, and this will be I because it is entering here. This will be I by 2 and this will be I by 2, and hence we have a situation where we have a vector like this, vector like this and vector like this, and the resultant of these three will be a vector which is like this. So from the previous position, so we can have this is the south pole and this is the north pole. So we have a situation like this. So it means the vector is rotating in the clockwise direction. All right. So this is how the vector is rotating, and after some time the vector will again rotate, and thus what we will have here, will have a continuous rotation, and the rotor will try to catch up with the stator field, and hence we will have a continuous rotation in the clockwise direction. So this is the connection for clockwise rotation. So if we can connect the phototransistor 1 to the base of transistor 6, phototransistor 2 to transistor 1, phototransistor 3 to transistor 2, phototransistor 4 to transistor 3, and phototransistor 5 to transistor 4, and phototransistor 6 to transistor 5, will have a continuous clockwise rotation of the rotor. And here we can see that at any given time all the three windings are excited, and hence the torque production is more compared to a unipolar drive. Now what about the counterclockwise rotation? So we will see how we can have a counterclockwise rotation. Let us again redraw the windings. This is phase A. We have phase B. We have phase C here. Now phase A is again connected to T1 and T4. Phase B is connected to T3 and T6. Phase C is connected to T5 and T2. Now here at this instant, the rotor originally was at this position. This is the north pole and this is the south pole. So here we would like to have the rotation in the anticlockwise direction or counterclockwise direction. So in that case, we expect that the stator MMF should be in this direction with this south pole and this north pole, so that the south pole here will attract the north pole of the rotor, and hence the rotation will be in the counterclockwise direction. So how to achieve that? Now to achieve that, we will have the current in the windings in the following fashion. So this winding will have current like this, this winding will have current like this, this winding will have current like this. So essentially what we have, we are having three vectors here. One vector is like this, the other vector is like this, the third vector is like this. So if this is, let's say, I, this is I by 2 and this is I by 2, and the resultant of these three will be in this direction. So what we have to do here is that we have to switch in such a way that the currents in the 3 windings will be I by 2 and I by 2 respectively. If one current is positive, other 2 currents will be negative. So here we switch in the following fashion. We switch here T4, and then this current is negative, so we switch T4 of phase A. Then for phase B we switch T3, and for phase C we switch T5. So this current coming out by convention we have assumed to be positive, let us say. So if the current coming out of the winding as per convention is positive, you can also assume the other way around, but here we have assumed that the convention of the current is positive when it is coming out of the winding. So in that case, phase A should be applied with a negative voltage, phase B should be applied with a positive, and phase C should be applied with a positive voltage. So here we can have the phototransistors like this: PT1, PT2, PT3, PT4, PT5 and PT6. So they should be connected to the respective transistors. And what are the various transistors? Now we say that we have T4 is on, T3 is on and T5 is on. So we will say this is connected to T3, this is connected to T4 and this is connected to T5. And similarly we will see here we have T6 here, T1 here and T2 here. So this is how we can connect the various phototransistor to various transistors, and this will result in the counterclockwise rotation. After some time we need to shift this MMF vector of the stator. So initially in this case, if we see the phototransistor PT1, PT2, PT3, PT4, PT5 and PT6, these were initially 1, PT1, PT2, PT3, PT4 was 0, PT5 was 0 and PT6 was 0. Now since the rotation is the counterclockwise direction, there is a little change in the pulse pattern. Now here this will shift left. So what we have here is this, that after some time PT1 will remain 1, PT2 will also remain 1, PT3 will be 0, PT4 will be 0, PT5 will be 0 and PT6 will be 1. Now in the second step, the first step is complete. In the second step, let us see what is the direction of the MMF, whether the MMF is rotating in the counterclockwise rotation or not. So PT1 is connected to transistor 3. So this is on. PT2 is connected to transistor 4, that's on. PT6 is connected to transistor 2, that's also on. So here what we have transistor 2, 3 and 4 are on. So if 2, 3 and 4 are on, what is the state of the MMF? So we will see that in the second situation we have the 3 phases here, again phase A, phase B and phase C. This is connected to T1 and T4, B is connected to T3 and T6, C is connected to transistor T5 and the transistor T2 of the inverter. And what we find here is that T2, T3 and T4 is on. If T2 is on, this is on, T3 is on, this one is on, and T4 is on means this is on. So it means the phase B is connected to the positive and hence the current will be positive, and by definition the positive current is coming out of the winding. So we can say that this is the current here, and T3 is negative. So, this is the nature of the MMF here, and T2 is also negative. So, we have the nature of MMF will be like this. So, here what we have in this case is that we have 3 vectors, one like this, other is like this, and the third one is like this, and the resultant of these 3 will be like this. So, we have seen that the resultant MMF in this case will be here, right, and this MMF is shifted from the original MMF by 60 degree, and this means the MMF is moving in the step of 60 degree. So, from the first position to second position, the MMF has rotated by 60 degree in the counterclockwise direction. The rotor will also try to catch up with this MMF, and hence the rotation of the rotor will be also in the counterclockwise direction. Now, let us see again what about the torque pulsation or the torque production here. Now, if we see the structure of this encoder and the rotor, we see we have 3 windings in the stator, phase A, phase B and phase C. The rotor is at this moment is vertically aligned. The disc is fixed to the rotor. The disc and the rotors are basically glued. The rotor is right now in the upward direction, north pole is facing up, and then the disc is fixed with the rotor. Now, at this instant, the MMF, as you have seen, is along phase A, because the angle should be 90 degree. So, this is the MMF of the stator, and the rotor MMF is vertically upwards, and hence naturally the stator MMF and the rotor MMF are aligned with each other at an angle equal to 90 degree, and this angle 90 is conducive for maximum torque production. Now, after 30 degree from this, the encoder is continuously moving in the, let us say, clockwise direction. So, after 30 degree, the encoder will be occupying this position. Okay. So, this will be occupying this position. So, this will be the opaque region, right, and will have this region as transparent region. Okay. So, this is the situation that we have, that PT1 is getting covered and PT4 is getting uncovered. So, PT2, PT3 and PT4 will give us high signals, and at this instant the MMF will be shifting by an angle that is equal to 60 degree. The next position of the MMF we have already seen will be along this direction. Okay, and this angle between these two MMF is 60 degree. So, the MMF changes in the step of 60 degrees, and in one revolution there will be 6 changes of the MMF, and hence we are expecting some torque ripples here. Now, what is the nature of the torque ripple? Now, at this instant, if you see that the rotor has already moved, what about the stator? I mean the rotor poles. The rotor poles will also be moving to this location. It is a new location, and the new location will be like this. This is the north pole and this is the south pole. So, right now the rotor axis is aligned along the stator MMF not at 90, but at 60, again 60 degree. So, this angle, if we see this position, this is the position of the rotor right now. After the disc has shifted through an angle 30 degree from the previous position, the rotor is also shifted along with the disc by the same 30 degree angle. So, this angle between phase A and the rotor, this angle is also 60 degree. So, at the commencement of the next switching, the rotor is aligned not at 90, but at 60 plus 60 equal to 120. and we know that the equation for the torque production T is equal to K some constant psi 1, psi 2 and the sine of the angle between them. Psi 1 is the rotor flux, psi 2 is the stator flux, and gamma is the angle between the rotor and the stator flux. So if the angle is 90, if gamma is 90, the torque is maximum. So we say that T is maximum for gamma equal to pi by 2. So we can say that, one of the fluxes will be, say for example, if psi 1 is the stator flux, psi 2 will be the rotor flux. And at this instant, when the state is changing, what is the angle between the rotor and the stator MMF? That angle is 120. So we can say that gamma initial is equal to 120. Gamma is not constant. Here gamma is changing. Gamma is changing with the rotor position because the rotor is not stationary. Rotor is moving away. Now the rotor is gradually moving away, and after again 60 degree, because this is the position of the current position of the disc. Now when the disc will come to this position, P2 will be covered and P5 will be uncovered. So the disc will have to travel through 60 degree for the next switching. So hence, if gamma initial is 120, gamma final is equal to 120 minus 60 degree, because the MMF will be stationary till the next switching, and the next switching will occur only after 60 degree. So up to the next 60 degree, the MMF will be stationary here, the stator MMF will be stationary. So gamma final will be 60 degree, and hence we can say that as the rotor rotates, gamma is continuously changing from 120 to 60, again jumping to 120 to 60, continuously like that. Of course the average is 90, 120 plus 60 by 2, so we can say that gamma average here is 120 plus 60 by 2, that is 180 by 2, that is equal to 90 degree, and that is conducive for maximum torque production pi by 2. But while the rotor is rotating, gamma is continuously changing, and hence we have a torque ripple. How does the torque change? The torque changes in the following fashion. We have the equation for the torque. We can say that T is equal to some constant K1 prime into sine of gamma, and with time gamma is also changing. We have this torque axis is in the y axis. So 120 to 60. So in fact the torque is changing as a sine wave, but it is changing like this. So this is gamma equal to 120 sine, then it decreases, becomes 90, where the torque is maximum. This corresponds to gamma equal to 90. So we can say this is for gamma initial, and this one is for gamma final, and since it is periodic, it is constantly changing. So this is the nature of the torque pulsation, and here we will have 6 safe torque ripples. So torque ripple is 6 times the frequency of revolution. Okay. So in every mechanical revolution we will have 6 times the torque pulsations. So this is sometimes not acceptable, but this kind of brushless DC motor drives are not used for very high performance application, because of the torque ripple, inherent torque ripple, they are only limited to fan type of application. So whenever we have a fan, we can go for a drive like this, and the torque ripples which is inherently present in this kind of drive doesn't do any harm for a fan drive. But for a drive like automobile or a traction application, we can't have this kind of torque pulsation. They will create vibration and discomfort to the passengers. So, so we can say that basically a low cost brushless DC motor applied application, in this case fan applications, and other application could be a pump application and so on. As we know that in any drive we would like to control the torque, and the torque is basically controlled by controlling the current. Now here we don't have any means of controlling the current, because we have applied a fixed DC voltage. Say for example, let's take a small fan, a 12 volt fan. We have applied a plus 12 volt battery, and we are not controlling the current. And if we want to control the current, we need to have a mechanism for current control. And this kind of drive are not current control, and hence they are applied only for fan and pump type of application, running essentially at constant speed. Now we will take little advanced drive. Let us see that we will take trapezoidally excited brushless DC motor drive with current control. Now let us understand what is a trapezoidally excited brushless DC motor. In brushless DC motor, the stator windings could be concentric, the stator windings could be distributed. I will show you some picture of. So we have, this is a brushless DC motor drive. This is the internal structure of the brushless DC motor. In this case, we have the rotor. In this case, we can see that they are the permanent magnets. We have in this case 1, 2, 3, 4, and then other 4 poles. So it's an 8-pole rotor. And the stators are having windings, and these windings are concentric windings. And the concentric windings are used for low cost brushless DC motor, which are used for fan application, pump application, and could be for any actuators, for electromechanical actuation system. We can have other type of structure. Now this is the structure of a brushless DC motor. The stator winding in this case is here. This is the stator structure. The stator core is laminated, and these are the windings of the stator, and the stator winding in this case is distributed. This is not concentric as we have seen in the previous case. This is a little more expensive brushless DC motor where the windings are distributed. This is a distributed winding. We have the slots in this case, and the windings are similar to that of a 3-phase synchronous motor. These are the overhang structures. This is the slot opening, and these are the stampings, and this constitutes the stator core. This is the rotor of a typical brushless DC motor drive, which is little more expensive and which can be applied for traction application and automotive application. And we have the magnets. The magnets are inside the rotor, buried inside the rotor, having interior permanent magnet structure. This is how the magnets are buried here. This is the rotor core. The rotor core is also laminated, and this is the magnet. One side could be a south pole, other side could be a north pole, and the fluxes will be coming out of the north pole and entering the south pole. And here the magnet is buried within the rotor, and hence we can call this rotor to be interior permanent magnet rotor. This is the assembly of the rotor and the stator. The rotors are having 4 magnets here. It is a 4-pole structure, and the stator is distributed winding, and this kind of windings are applied for high performance application that we are discussing right now. So, coming back to our original discussion on a trapezoidally excited brushless DC motor drive. Now, let us discuss a trapezoidally excited brushless DC motor drive. What is the meaning of trapezoidally excited system? In trapezoidal excitation, the back EMF of the motors are trapezoidal in nature. Now, this is produced in a winding having distributed structure as follows. The rotor in this case is here, we have the rotor, and then we have the stator. The stator core structure is like this. So, we can divide this into 6 segments, and the magnet is arranged in the following fashion. This is the magnet. So, other side also we have a magnet here, and in this magnet we have 2 poles, one pole and other one is the south pole. So, this is the rotor core, and here we have the magnet. It is a surface mounted structure. So, we can show this magnet in a hashed fashion. The stators will be having 3-phase windings, and the windings are distributed over the stator structure. The stator inner surface is a cylindrical surface. So, we have the slots, and in the slots we can have the windings, and the windings are in the following fashion. We have the windings, and we are now seeing the cross section of the conductors. This is for phase A, and phase A return path is here. So, if we have dots here, the current is coming out. In this case, here the current is going into cross. This for phase A, and phase B is shifted from phase A by 120. So, we can have the structure of phase B. Phase B is here, this phase B, and we will have the B prime, and similarly we will have phase C, and we have the C prime. So, the windings are distributed over 60 degree. We can see that this angle here is 60 degree. So, as the rotor rotates, suppose the rotor is rotating in the counterclockwise direction, this is the direction of rotation, we can say this is the omega r, and as the rotor rotates, the induced EMF in a phase will be trapezoidal in nature. Now, if we see the nature of the induced EMF, we will see that the induced EMF in phase A will have a structure like this, This will have a structure so this we can say A, phase A. When the magnet is entering the winding, the induced EMF is gradually increasing from negative to positive. Here the winding was under the influence of, let us say, north pole, phase A winding, and gradually the north pole is going away and south pole is entering the winding. So the EMF is gradually changing the polarity, and then the winding is fully under the influence of the south pole. Then again the north pole is entering and the polarity is gradually reversing, and here we have full north pole. And thus we see that the induced EMF in each phase is not sinusoid, it is basically a trapezoidal structure, and hence we call this to be a trapezoidally excited brushless DC motor drive. In the next lecture we will try to see how we can have current control for this trapezoidally excited system, and how we can also dynamically model a brushless DC motor drive with trapezoidally excited induced EMF.